Hello everyone, my name is Miao. I'm from Icahn School of Medicine at Mount Sinai. My title is Reactomics, using mass spectrometry as a chemical reaction detector. I know it's another omics, but I think this one will make your life easier. So let's first review some typical workflow for high-resolution mass spectrometry metabolomics. At the very beginning, we collect samples and then make sample prep treatment and then acquire data using mass spectrometry. After we get the peak list of features, we annotate those for identification with the compound's name. And then we will build the links between the compounds using pathway or network analysis. So in summary, the whole process is like samples to peaks and peaks to compounds and compounds to the relationship among compounds. So in most cases, the final purpose is to find the relationship among the compounds. There are two problems for this typical workflow. The first one is time consuming. Usually for each samples, we can collect more than 20,000 peaks or features. There are too many peaks. If we want to check it one by one, it's almost impossible. Another thing is the standard coverage. When we want to make some identification from peaks to compounds, we all rely on some known database or some prediction algorithm based on some known database. So in this case, it's really hard to find some unknown compounds. So here is my idea to solve these problems. Let's look at this workflow: sample, peak, compound, relationship among compounds. If our purpose is the relationship among compounds, could we directly measure it from the peaks and skip the annotation of the compounds? Actually, it could do. For example, if there is an oxidation process happen, we will always see a delta 16 Dalton between the parent compound and their product compound. Here I mean different compounds, not the ASMS spectrum. And if we use mass spectrometry to measure all the mass charge ratio of all the peaks, we calculate the paired mass distance, we may find this. And in this case, the mass spectrum could directly measure such relationship, and I call it reactions. Why reactions? So let's go back to see our study from the genomics. The genomics is based on only 5 gene, is 80 GCU. And then we came to the proteomics is only 22 unit, as I listed here. Why they are more acceptable for analytical chemists? Because we actually don't need to make identification of this unit. We just need to care about the combination. For example, the genes combination is a base pair, and for protein, the combination is a peptide bond. But what's the base pair for the molecule, for small molecule? Here I think the small molecular combination is a reaction or chemical reactions. In terms of mass spectrometry, it's paired mass distance. So why is paired mass distance? When an atom is formed, it will lose a certain amount of nuclear binding energy. So this missing mass will transferred from atom to the mass distance between compounds. If we have high resolution mass spectrometry, we can find this paired mass distance very unique. Not very, it's just unique to a specific element composition, so that we can use it for annotation. So, but we need to clear that the PMD is not only generated between compounds, it can also generate within compounds, especially in the mass spectrum. For example, the isotope will always from one compound will generate multiple peaks. Another is insult reactions. Different adults, there will also be a paired mass distance and also structural similarities like lipid. But here in this, in terms of reactomics, we only care about the reaction relationship among different compounds. So could we build a database of that PMDs? I think so. So as a quantitative analysis of reactomics, I analyze all the reactions from KEGG reaction database. And here you can find the first one, is actually a double bond breaking or forming process. There are almost 2,000 peaks, 2,000 reactions were involved in these PMDs. It's almost 15% of all of the reactions in the database. So here we see an interesting phenomenon that the reactions are actually enriched by a few PMDs, which make it very easy for us to perform some quantitative analysis. We do not need to deal with a lot of unknown things. In most cases, if this is a certain samples is from biological system, it will have this enrichment phenomenon, and it can also be linked to some reaction classes or enzymes. So when we have the annotation of the element composition, the next step is how do we make a quantitative analysis of these PMDs. Here, in terms of mass spectrometry, we need to know that the mass pair always means two mass charge ratios. So if we want to make quantitative analysis, the ratios between these mass pairs should be stable across all the samples. So here I propose the concept about static and dynamic paired mass distance, and we can only use static paired mass pairs for PMD quantitative analysis. For example, we can say A, B, C, D, E, F, they are mass pairs involved in the same PFDs. But for two samples, AB pairs and EF pairs, their intensity ratios is always the same. So we can use them for quantitative analysis. But CD pairs, since they are changing in different samples, we can't use it. As we have the method to quantitative and quantitative analysis of reactions or PMDs, let's see some applications. First one is metabolite discovery. So metabolite discovery is usually happen in two kinds of research. One is the environmental polluting metabolites discovery, another is drug metabolites discovery. In general, there are some exogenous compounds, and it's always involved in a specific pathway called symbiotic metabolism. And there are phase 1 reaction and phase 2 reactions. And as you can see here, for the common phase 1 or phase 2 reactions, we can all calculate a specific PMDs for them. For example, the oxidation is almost 16, and the methylation is more 14. To make it clear, let me show you an example. This is a published work, which I also involved. Is about to find some metabolites of terabromo bisphenol A. TBBPA, to find the metabolites in pumpkins. And first we use mass defect analysis to screen all the brominated compounds, and then we actually manually check it one by one. We find 7 different metabolites, and then confirmed by synthesized standards. But when I check the results, I find an interesting phenomenon. As you can see here, the first metabolite is just add a is a glycosylation process of the original compound. The second one is add another functional group, and this one add the glycosyl group in both sides. So it's like step by step. So I think we may still missing a lot of potential metabolites. As we check these results, there must be some paired mass distance can be applied in this study. Then I get the raw data of this study and I perform again on those data, and I build a network, a PMD network of TPBPA, use the 5 process which already reported in these 7 different metabolites. And interesting, we not only find all the compounds we found before, we also find some the metabolites of metabolites of metabolites of metabolites of metabolites of metabolites of TPPPA. So it means by a local recursive searching strategy, we can actually find all of the possible metabolites within the dataset. So this is the first application of reactomics, is to screen all the possible metabolites. The second one is to find whether a compound is endogenous or exogenous. So this is a very difficult problem. For example, if we have a untargeted analysis of environmental samples, we want to know whether a certain peak is from the exposure or it's just from an endogenous process. So, for example, if we find some interesting compounds from the urines, we need to know whether this compound is just from the exposure or is from some genetic driving process or endogenous compounds. So the first thing I did is also the data mining. I only find T3DB. This database has the annotation of whether a compound is endogenous or exogenous. I collect all these endogenous compounds and exogenous compounds and pull them together. And to simulate the real samples, we just use the top 10 high frequency PMD. We didn't use a PMD set that predefined. And then we build a network as we can show here. The red one is all the endogenous compounds, and the blue one is exogenous compounds. And here is very interesting. You can see that most of the endogenous compounds, they are coupled into a larger network, while the exogenous compounds, only few of them are in this big network, and most of them are just isolated with each others. So is this a way to distinguish whether a compound is endogenous and exogenous? Then I go back to the KEGG database. I specific check 4 compounds. It's glycine, colistin, caffeine, and bromophenol. And the first 2 are endogenous compounds. If we build the PMD network by the top 10 high frequency PMDs within KEGG database, we can find the network is quite large and quite complex structures. But when we go to some exogenous compounds, we can see the network structure is quite simple. It's reasonable because endogenous compounds are always the base of our biological system, and our biological system will have the enzyme to make this reaction happens. But for exogenous compounds, because they are just they are not that universal in the environment, or they may be man-made, so our human system or the biological system may not have a specific enzyme system to metabolize them. So that's why their network is much shorter. So in this case, we may have a way to distinguish whether a compound is endogenous or exogenous. We just calculate what I call it average network distance of the compounds. For example, the average network distance of TBBPA is around 4, and the network structure complexity is just in the middle between the endogenous compounds and the exogenous compounds. If you check the real data is also like this one. If a compound coupled into a network with average network distance larger, it means in most cases it's endogenous compounds. But if they are isolated, and in most cases we can say that it's exogenous compounds. So the third application is more about medical research. In most cases, our collaborator, when they talk about metabolomics, they're always thinking, oh, I want some biomarker. When they say biomarker, it means biomarker compounds. But in reactomics, we think the biomarker could not only be a compound, but also be reactions or specific PMDs within the data. So here I will take an example from the public data set. This is, if you search this MTBL S28, you will find it online. It's about a lung cancer data set with 1005 human urine samples. And after I get this data, I check the high frequency PMDs as well as some non-PMDs from the CAC database that we are sure they have a relationship with reactions. And then we find the PMD 2.02 Darden, which is a double bond broken forming process, show a significant differences among control and cases. And the cases always has a lower activity of these reactions. So in these cases, I think the biomarker reactions may work is not to rely on one compound. At least it will rely on two compounds. I think if we can get more information from more peaks, the result may be more reliable. So all of the previous study or research can be done by software I developed. It's PMD package. It includes global STD algorithm which used to reduce the redundant peaks to find only one peaks for specific compounds, and then perform the PMD based on that peaks. And it also has a PMD reaction databases based on CAG and HMDB. You can also perform the quantitative PMD analysis and network analysis by this package. And also, actually, I didn't mention here, but you can make the MS-MS annotation based on PMDs. If you show interest, you can check our poster at the list here. And for another related package I developed is IMWF package. It included some real data from our lab, and it also has an R Markdown tablet which you can follow the data analysis step by step from the raw data to the final report. It's also part of Docker image, which contains the same open source data analysis software and interface in our lab. We have 4 take-home messages. The first one is reaction is the base pair for small molecules. The second is reactomics means the omics study at reaction or PMD levels. The third one is real data always enriched in few PMDs or reactions. The last one is reaction level changes could be quantitative and predictable. At last, I want to show my thanks to the Institute for Exposed Mix Research from Icahn School of Medicine and Mount Sinai, and our Department of Environment, Medical and Public Health. I'm a postdoc from Dr. Patrick's research group, and this is our group pictures. I also want to show thanks to Dr. Xinwang He, who gave me the raw data of TPPPA. And if you have any questions, feel free to contact me via this email, and I will also be in the live Q&A session. Thanks.